Robotics is the interdisciplinary field of science and engineering focused on the design, construction, operation, and use of robots. Robots are automated machines that can perform tasks typically done by humans, often in environments or under conditions that are dangerous, repetitive, or highly precise. In robotics, the system is typically composed of hardware, middleware, and software components, each serving distinct but interdependent roles. Hardware components are the physical components that make up a robot and enable it to interact with the environment. Let's break down the main hardware components that make up a robot and their applications. Mechanical components. These form the robot's structure, including parts like arms, joints, or the chassis. They allow the robot to physically interact with its environment, like an industrial arm assembling products or a drone's frame for flight. Sensors and perception systems. These are the eyes and ears of the robot. Sensors like cameras, LiDAR, or ultrasonic sensors collect data about the robot's surroundings. They help the robot understand its environment, detect obstacles, and navigate autonomously. Think of the sensors in self-driving cars or robots that map out rooms. Actuators. These components enable the robot to move or perform actions. Motors, hydraulic actuators, and servos convert electrical signals into mechanical movement. For example, in robotic arms or drones, actuators move parts, joints, or wheels. Power supply. Just like any machine, robots need power. Batteries or fuel cells provide the energy needed to run the robot's sensors, actuators, and control systems. This is similar to how a drone relies on batteries to fly. Communication system. The communication system allows different parts of the robot to talk to each other and sometimes communicate with humans or external systems. This could be through Wi-Fi, Bluetooth, or even 5G. For example, industrial robots use this system to send data to a central server or control station. Control units. These are the brain of the robot. They process data from the sensors and decide what actions to take. Whether it's a small microcontroller in a simple robot or a powerful computer for a complex drone, control units manage everything from movement to decision-making. Locomotion system. This is how the robot moves. Robots can use wheels, legs, tracks, or even propellers. For example, a robotic vacuum uses wheels, while a walking robot might have legs to navigate more difficult terrain. Environmental systems. These systems help robots interact with their environment. For instance, temperature or humidity sensors help robots perform tasks in dynamic environments, like agricultural robots that monitor crops, or factory robots that adjust based on conditions. Safety and emergency components. Safety systems ensure the robot operates without causing harm. Emergency stop systems, safety sensors, and redundant controls help protect both the robot and its surroundings, particularly in industrial settings. So these hardware components work together to give the robot its functionality, enabling it to perform tasks autonomously or interact with humans, industries, or environments efficiently and safely. Software governs the logic, behavior, and decision-making processes of the robot. This is where the intelligence of the robot resides. This is comprised of control software, perception software, AI and machine learning, path planning and navigation, human-robot interaction, simulation software, safety software, and task management and coordination. What does a control software do? It calculates the control input from the robotic system state. The control input can be torque, velocity, or position. This control input is what moves the actuators of a robot. There are different strategies or controllers used to calculate this control input. For example, a PID controller is used for simple linear systems. Advanced controllers like model predictive control or adaptive control are used for linear systems with more constraints. For non-linear systems like for a self-balancing robot or a quadrotor drone or an airplane, feedback linearization or Lyapunov-based control is implemented. Perception software is the part of a robot that turns raw sensor signals into usable information about the world. Sensors like cameras and LiDAR produce pixels and distance readings, but those raw measurements don't directly tell the robot where obstacles are or what objects it is looking at. Perception software synchronizes and calibrates the sensors, filters noise, and then estimates structure such as depth, free space, and obstacle geometry. It can also detect and classify objects, like people, pallets, or tools, estimate their position and orientation, and track them over time. Perception and navigation are directly connected. Perception builds the robot's understanding of the world, and planning navigation uses that understanding to choose safe motion. Perception takes raw sensor data and produces usable outputs like a map of free space versus obstacles, for example an occupancy grid, a 3D model of the surroundings, a point cloud, and sometimes object positions in motion, like where a person is and where they are moving. Path planning then uses this information in two main steps. First, the global planner uses the map to decide a route to the goal. For example, if the occupancy grid marks certain cells as occupied, because perception detected shelves and boxes, the global planner searches through the free cells to reach the target aisle without crossing obstacles. Second, the local planner uses the latest perception updates to react in real time. For example, perception detects a moving person and reports their position and velocity. The local planner uses that to slow down, keep a safe distance, steer around them if there is space, or stop if the path becomes blocked. Finally, navigation produces a trajectory. a sequence of desired positions and speeds that respect constraints like maximum turning radius and acceleration. Control then converts that trajectory into motor commands. So the chain is, perception updates the world model, planners use that model to compute a safe path in motion, control executes it. Without perception, planning doesn't know what to avoid. Without planning, perception doesn't become purposeful movement. AI and machine learning in robotics software provide data-driven capabilities that are difficult to achieve with hand-coded rules. In perception, machine learning is used to recognize and localize objects. For example, a camera image can be processed by a neural network to detect a person, a pallet, or a tool, and output their position or bounding region. This is required because real environments vary in lighting, clutter, and object appearance, and fixed thresholds or simple geometry often fail. In navigation, machine learning can predict the motion of dynamic obstacles. For example, if perception detects a walking human, an ML model can predict where that person is likely to move in the next few seconds. The planner then uses that prediction to slow down early or choose a path with a larger safety margin. In manipulation, machine learning can estimate good grasp points on unknown objects. For example, from a depth image, a model proposes grasp poses with success probabilities, and the robot selects the most reliable grasp that is collision-free. Machine learning can also detect anomalies and faults. For example, if motor current and temperature patterns look abnormal compared to normal operation, an ML model can flag a potential failure so the safety system can stop the robot before damage occurs. In many real robots, ML outputs are treated as probabilistic estimates, not absolute truth. The system attaches confidence scores, checks safety constraints, and falls back to simpler methods when confidence is low. So the practical purpose of AI and machine learning is to increase robustness and capability in complex, uncertain environments, while the rest of the robotics stack enforces safety and physical feasibility. Human-robot interaction is the part of robotics software that manages how humans and robots communicate, coordinate, and share control. It is required because robots operate around people, and the system must be understandable, predictable, and interruptible, especially when autonomy is uncertain. HRI software typically has three functions. First, it provides input channels for humans to specify goals or intervene. This can be a touchscreen, joystick teleoperation, voice commands, gesture input, or a remote control interface. For example, a warehouse operator can tap "Go to aisle 4" or take manual control to reposition the robot in a tight space. Second, it provides output channels, so the robot communicates intent and status. This includes visual displays, lights, sounds, projected pads, or spoken messages. For example, a delivery robot can indicate "I will pass on your left," show its planned route on a screen, and signal when it is stopping or turning, which reduces surprise and improves safety. Third, it supports shared autonomy, where the human provides high-level intent, and the robot handles low-level execution with safety constraints. For example, a human selects an object to pick, and the robot plans a collision-free arm motion and performs the grasp while monitoring contact forces. If confidence drops or a safety limit is approached, HRI can request confirmation, switch to teleoperation, or pause. In well-engineered systems, HRI is tightly connected to safety and task management. Human commands are validated, unsafe commands are rejected or modified, and the human can always trigger a safe stop. The core purpose of HRI software is to make robot behavior controllable, interpretable, and safe when operating with or near humans. Safety software is the part of a robotic system that prevents hazardous behavior even when other modules make mistakes or hardware faults occur. It acts as an independent supervisory layer that enforces hard limits and triggers safe states. In practice, safety software does four main things. First, it enforces physical limits. It clamps or blocks commands that exceed safe bounds: maximum speed, acceleration, torque force, joint limits, temperature, current, and battery constraints. Example, if navigation asks for a fast turn near a shelf, safety caps the angular speed to a safe value. Second, it monitors the environment for immediate danger. It uses perception-derived signals, like minimum distance to obstacles or humans, to maintain protective zones. Example, if an obstacle enters a protective stop radius, safety overrides motion and commands zero velocity or braking, regardless of what planning wants. Third, it detects faults and timing failures. It checks that critical loops run on time, watchdogs, sensors are healthy, and estimates are plausible. Example, if the control loop misses deadlines or the IME stops updating, safety transitions the robot into a safe stop because the state is no longer trustworthy. Fourth, it manages safe state transitions and recovery. Safety defines what safe means for the platform: controlled stop, brakes engaged, power cut to actuators, or moving to a safe pose. Example, for a robot arm near humans, safety may switch to a low torque mode and retract to a known safe posture. Task management and coordination are the parts of robotics software that decide what the robot should do, in what order, and how to handle failures. They sit above perception, planning, and control, and they turn a high-level mission into a reliable sequence of actions. Task management is required because real robotic work is not one continuous motion. It is a multi-step procedure with conditions. For example, a warehouse robot's task might be navigate to shelf A, confirm the correct item, pick it, verify the grasp, navigate to the packing station, and place it. If any step fails, like the item is not detected, the grasp slips or the path becomes blocked, task management chooses what happens next. retry, choose an alternative grasp, replan, wait, or request human help. This logic is often implemented using state machines or behavior trees. Coordination is required when multiple robots or multiple subsystems must share space and resources. For example, in a fleet of delivery robots, coordination assigns each delivery request to the best robot based on distance, battery level, and payload capacity. It also prevents conflicts. Two robots shouldn't enter a narrow aisle from opposite ends in deadlock, and they shouldn't all queue at the same charging dock. Coordination manages scheduling, traffic rules, and resource reservations, so the whole system stays efficient and safe. So task management ensures the robot completes a mission reliably with recovery behavior, and coordination ensures multiple robots work together without collisions, deadlocks, or wasted effort. Simulation software is the part of a robotics workflow that lets you test and develop robot behavior in a virtual world before running it on real hardware. It is required because real robots are expensive, slow to iterate on, and unsafe to use for trial and error, especially when you are tuning controllers or testing new navigation and manipulation behaviors. Gazebo and NVIDIA IsaacSim are examples of simulation softwares used to test the robotic software. Here's a concrete example. Before deploying a new obstacle avoidance algorithm for a warehouse robot, engineers run thousands of simulated runs with different aisle layouts, moving people, sensor noise, and slippery floors. They measure outcomes like collision rate, time to goal, and stability of control. If the robot clips obstacles or oscillates, they adjust planner parameters or controller gains and retest immediately, without risking damage. Simulation is also used to generate training data for machine learning and to perform regression testing. Every time the software changes, the robot is retested in the same scenarios to ensure performance did not degrade. Middleware is the software layer that connects all the different parts of a robot. A robot is not one program. It is many programs running at the same time: perception, localization, planning, control, user interface, and hardware drivers. Middleware is required because these modules must exchange data reliably, in real time, and often across multiple computers. It provides standard communication methods, like message streaming, request-response calls, and long-running goal execution, so modules can be developed and replaced independently. ROS, the Robot Operating System, is the most common middleware-based framework used in robotics. ROS organizes the robot software as a network of processes called nodes. Each node performs one function, and nodes communicate using standard interfaces. The most common interface is a topic. One node publishes messages, and other nodes subscribe. For example, a LiDAR node publishes laser scans, a perception node subscribes and publishes detected obstacles, a localization node publishes the robot pose, a planner node subscribes to pose and obstacles and publishes a path, and a controller node subscribes to the path and publishes motor commands. ROS also provides services for quick request-response operations, like resetting a map, and actions for tasks that take time, like navigate to this goal, with feedback and the ability to cancel. So middleware is what makes modular robot software possible, and ROS is a standard ecosystem that provides that middleware, plus the tools and conventions to build, run, and integrate robotic systems. To summarize, robotics is an integrated system. Hardware provides sensing and actuation, software provides perception, planning, and control, and middleware such as ROS connects these modules into a reliable, real-time architecture. When these layers are designed with clear interfaces, safety supervision, and robust testing through simulation, the result is a robot that can operate predictably in complex real-world environments.